Okay, so today we're going to talk a little bit about some geometry that I would hope that you would already know coming into engineering, but we're going to be a little bit more realistic and recognize the fact that some of this is, it's ancient history, or, you haven't practiced it enough or whatever. Just, maybe it's just a hole in your education, and that's totally fine. We all have holes in our education. So what we want to do, though, is we just kind of want to gather in one place all the geometry that that could pop up. And typically on this talk, most of this is going to be trigonometry. But hopefully this will be a pretty short video. So I'm not really going to get into too much more than that. But the trig is the biggest thing that I see that my students have issues with. So we're going to start with trigonometry, which is nothing really fancy. Trigonometry, it tends to freak people out a little bit. I guess it's a annoying word, but it just means we're just measuring triangles. Okay, that's all we're doing. So we're going to talk about triangles of two different types, basically right triangles and all triangles. All right, so I've drawn, just two triangles. One is just the any triangle and one is the right triangle. And what we're going to think about with respect to these triangles, is we want to think about angles and sides, and inevitably we always want to find different angles and different sides. So the first thing that happens for any triangle, and I should note that the right triangle is just a special case of the any triangle. So you can always, so anything you can apply to any triangle, you can apply to the right triangle. So we're going to start with thinking about the angles. And typically, that is disappointing. Okay, let's move that back to where it was, more or less. And let's, okay, so, so if this is angle alpha, this could be angle beta, and this could be angle gamma. Okay, and these are just Greek symbols. And so alpha kind of goes across with A, beta goes across to B, and gamma goes across to C. Okay, so gamma is the third letter of the Greek alphabet. Okay, so basically there's a few things that we should note here. One is that alpha plus beta plus gamma equals 180 degrees. Okay, that's always. Okay, or if you prefer pi radians. Okay, just, however you want to do it. I'm going to switch to a darker color. I think it'll show up a little bit better here. That's not the best color right there. Okay, so that's one really important thing to know. It'll help you figure things out whenever that pops up. The other thing that happens here is what we call the law of sines. The law of sines, and we'll talk about what a sine is in a second. Right now, for the any triangle side of things, we just think of it as this kind of magical thing that just kind of works out. And basically it's comparing A, the ratio of side A, to the sine of the angle across from it, noting that A is here and the sine of the angle is across from it. Okay? And we're going to say that equals B over the sine of beta. Okay, so again, here's B, and here's the sine of, and here's beta, or the sine of beta, and it's the angle that's across from it, equals C over the sine of gamma. Okay, and again, noting that those are across from each other. Okay, so if you know, an angle and what's across from it, and you know anything else in the triangle, like if you know these, if you know A and sine of alpha, then you can solve, and you say beta, then you can solve for B. Okay, and so that's a really nice property that just helps out. And then again, and of course, if we're working with the law of sines, we need the law of cosines. Okay, and the law of cosines is so the way we've kind of drawn this up here, we're gonna do it as let's just do it the way it's typically written is c squared equals a squared plus b squared. So that should look familiar. Minus 2 a b cosine of gamma. Okay, so this is an interesting thing. So hopefully when you look at this, the first thing you're noticing is that the first bit of this is the Pythagorean theorem, which actually I'm going to put over here. Pythagorean theorem, because the Pythagorean theorem only applies to right triangles. But what we note here is that so I'm gonna kind of circle in red what we're talking about here. We're looking at a squared and b squared. So that's b is right here and a is right here. And then a, b, and gamma. Okay. So note that the entire right-hand side of the equation, these are kind of in order, side, angle, side. Okay, so there are three next to each other, and what you're solving for is the one across from them. Okay, so you're solving for this C, which is across from basically from that angle. Okay, and so that's just kind of an important thing to be aware of. Okay, so these are kind of the most important things that work for any triangle. Now, right triangles are nice because, so we're going to kind of move over to right triangles. And right triangles have a couple of special properties. So one of the cool things about a right triangle, is that we don't ever have to name this angle. Okay, this is the right angle. Okay, and we don't have to name this side. The side opposite the right triangle is always the hypotenuse. Okay, it's a fancy name. Who knows where it came from? Okay, and so the other two angles, I'm just going to call this one alpha and this one beta. Okay, and these sides don't really get names. I mean, we will go ahead and I'm going to give them variables, but they don't have a name, right? The only side in all of this that has a name is the hypotenuse. All the other sides are just A's, B's, or C's. But the hypotenuse, we're not going to call a letter. Maybe for simplicity, we'll just call it C for this. But basically, it's the hypotenuse. Okay? So one of the cool things about a right triangle is that what somebody noticed is, and I don't know who this person was, but what they noticed was that if you look at this triangle, and let's suppose you wanted to draw another triangle that was like, oh, that's not what I wanted to do, but it does demonstrate the right idea, is that if you wanted to, I'm not really going to be able to make it get bigger, I don't think. So if you wanted to make it twice as big, so if I made this thing huge, okay, notice that by doing that, I made the hypotenuse, 4 times as big, but I also made A 4 times as big and B 4 times as big, okay? And no matter how I move it or shake it or do whatever it is that I do to it, okay, the ratio of those sides, the ratio of A to B remains the same. The ratio of, please turn for me. Okay, thank you. The ratio of, the hypotenuse to A always remains the same. So what somebody noticed is they said, okay, so if that is the case, okay, then we're going to come up with some special rules to say that basically if we have a right triangle, if I know these angles, or if I know one of the angles, because of course if you know one of these angles and you know it's a right triangle, then you know the other one. But they said, well, look, if I know this angle right here, okay, or if I know this angle right here, I can say some things about the ratio of these sides. Okay, and so what they said is, and they gave it fancy names, but they said that, for a triangle with a given beta, okay, they knew that the ratio of, say, doesn't really matter, but we're going to try to do this in order. B over C is always the same. Okay, if you know beta and you know it's a right triangle. Okay, and if you know it's a right triangle and you know beta, then you can also say, okay, that A, the ratio of side A to the hypotenuse, is always a certain value. Okay, and then you could also go on and you could go one further, and you could say, well, if you know beta, then you could say that the ratio of these two other sides, so that would be, in this case, B over A, are always the same. Okay. Now, they could have used different ratios in this. These were just the ratios that they used. Okay. And so they gave these things things a name, and they said, well, I want to know what that ratio is. And so they called this a function. The function is called a sine or a cosine or a tangent. Okay. And it says that basically if you know beta, these two sides are going to have, the sides are all going to be in fixed ratios to each other. Okay? So in this case, so the sine of beta, so we're going to work with beta here. Okay? It equals B over C. So that is the side opposite of the angle to C, which is the hypotenuse. Okay? And then if I'm doing the cosine, well, A, that is not the opposite. That is the side adjacent. So basically there's, you always have to identify your sides. And the adjacent is the side that is next to the angle that is not the hypotenuse. So, this one is also next to it, but it's the hypotenuse, so we don't use that one. Okay? So then we've got what they call the adjacent over C, which is the hypotenuse. And then the tangent is the one that doesn't use the hypotenuse. So we're using the B, which is across, which is the opposite, over the, not the hypotenuse, excuse me, the adjacent. Okay, and so this is the way that we always remember this. The way this is usually taught is sine opposite hypotenuse. So that's so, and then cosine adjacent hypotenuse, ca, and then tan opposite adjacent, toa. Okay, SOHCAHTOA. Oh, not, SOHCAHTOA. SOHCAHTOA. Okay, so and this is probably the most important thing. It's the most important building block to all of your engineering. I still get students that, miss this, and my guess is if you understand this inherently, then versus someone who doesn't understand it at all, it's probably a difference of probably a letter grade and a half on every class in engineering. Okay. In fact, I actually think there should be no way for you to get through it without knowing this. So if you don't know this, if it's unfamiliar, then just work on it. Okay. Just, fight through it, because it's, don't just go, I don't really, just wave your hands and say, this is really important. Okay. Every time this shows up, make sure to kind of work on it. Eventually it will make sense. Okay. So we can also do this, I should note, with the other angle over here. So I could, if I wanted to, do it with alpha. Okay. Noting that in this case, the opposite is A. Okay, so this is the opposite side, and the adjacent side is B. Okay, and the hypotenuse is still C. Okay, so if I wanted to do it with alpha, I would say the sine of alpha equals, let's see, the opposite, A, over hypotenuse, C. The cosine of alpha equals the adjacent, B, over the hypotenuse, C. And the tangent of alpha is going to be, the two sides that don't apply, starting with the opposite. That they're not the hypotenuse, so we'll have A over B. Okay, so that's SOHCAHTOA, the most important thing that we will do here right now. Okay, and it's just about recognizing those ratios of those sides. Okay, anyway, so now that we have that, let's go down here and let's talk about this Pythagorean theorem, because when you are dealing with a right triangle, okay, we never use the law of cosines in that case, although the law of cosines is really great. But what we'll notice is that if the angle here, so let's see here, c squared equals a squared plus b squared minus 2ab cosine gamma. Okay, so the gamma on this triangle right here, okay, remember the gamma is the angle across from c squared. So here's c right here. The gamma right here, if it had a gamma, would be 90. Okay? The cosine of a 90 doesn't really make a whole lot of sense. Like if I go down to, with the cosine of a 90, well, let's see, an adjacent, there is no adjacent to this angle, okay, or hypotenuse. So it doesn't really make a whole lot of sense. But, however, if you plug it into your calculator, it will tell you what the cosine of a beta is, and it will tell you that the cosine is 0 of a 90-degree angle. And I'll kind of talk you through how you can think about that logistically. Okay, so basically if we were to plug that in over here, if I said, well, c squared equals a squared plus b squared minus 2ab cosine of 90. Okay, so if you plug into your calculator, the cosine of 90 is 0. So all this goes away, and you are left with the Pythagorean theorem, which is that the hypotenuse squared equals a squared plus b squared. Okay, and that's one of the most important things that happens in all of, math. Okay, so commit that to memory, know it forever, et cetera, et cetera. Okay, so how would we think about what that cosine of 90 is? Okay, and here's something that, I don't know, they bring up all the time when you're, they teach it to you in geometry, and I feel like they don't really tell you what it is that they're doing. So let me draw this out for you. This is a circle, and you guys may know this as like a unit circle, okay? And this is really an aside. It's not really critical for this course that you understand this unit circle. However, it does, I remember memorizing this unit circle and not having really any idea what it was we were doing, okay? And what the unit circle is, it's a collection of triangles, okay? Now I'm drawing this poorly because I'm doing this quickly, but notice that these are all triangles, okay? Now they all have the same bottom or base, okay? And if you remember correctly from your classes when you were in high school, okay, they always drew the angle going this way, and you were required to memorize certain values on here, right? I think hopefully you can remember that. You were supposed to remember that, a value here was something like root 3 over 2 comma 1/2, right? And that was for an angle of 30 degrees. So if this angle was 30 degrees, then that's what you would get, okay? And then if you had an angle, let me zoom in on this a little bit. If you had this angle right here was 45 degrees, then you would remember root 2 over 2 comma root 2 over 2, okay? And then you would remember values here, which would be 1/2, and this was for 60 degrees, 1/2 comma root 3 over 2. Okay, now what are these values and what is all this coming from? Okay, and these are sines and cosines and of that angle. So this guy right here, okay, this is the cosine of that angle of 30, and this one right here is the sine of 30. Okay, and it's like, well, what does that even mean? Well, in this case, these are sides of a triangle, okay? Because this is the y value of here. So this is 1/2 tall, okay? And this is the x value, okay? Root 3 over 2. Root 3 over 2 for a triangle whose hypotenuse is 1. Okay, so that's where this all comes from. Okay? And so what does that mean? Well, this means that if I said, well, what is the cosine of this angle, 30 degrees? Okay, well, I would start with the angle, and I would say, okay, cosine, adjacent, so that's this guy, equals root 3 over 2, divided by the hypotenuse, which is this guy, 1. So this is root 3 over 2. Okay? And of course, we could do the same thing with the sine, except we would have 1/2 over 1. Okay, because the cosine, or we could even get the tangent if we wanted. Okay, so what's the power of this? Why do we have this? Well, the point of this is that this works for, any triangle. And what we would do basically is, let's suppose instead of having a triangle whose hypotenuse was 1, I had a triangle whose side was 100. Okay, well, what would I need to do here? Well, I would need to multiply this by 100, multiply this by 100, and boom, I've got it, right? This side is going to be 50, and this side is going to be whatever root 3 over 2 times 100 is. So 50 root 3 is going to be this side, okay? And that's the power of this, okay, is that it's all about similar triangles and just having an easy way to understand the ratio of these sides. Okay, so I know that no matter what this thing is, if this is a 30 degree, if this angle is 30 degrees, this one is 1/2 of that. Okay, this is 100, this is 50. If this is 1,000, this is 500. Okay, and this is whatever that comes out to, 866 or whatever it is. Okay, I don't remember the calculator approximation. Anyway, but that's what the idea behind this unit circle is. Okay, so that's just a little bit of an aside. Okay, so let's go back, and I think we've got all the triangle stuff I wanted to cover. So then, real quick, let's do some angles. And we will not use that red. Red is not my favorite color. Whoa. Whoa. Okay, let's turn that into an E somehow. All right, angles. All right, so there's a few rules with angles. And they're pretty straightforward. I'm not even going to bother worrying about my lines being straight here. So here's an angle, alpha. Here's another angle, beta. This whole combined angle is a right angle. Okay, then alpha plus beta equals 90 degrees. Okay, these are called, I believe, they're called complementary angles. I don't care if you know the names of them. Okay, the other possibility is we're going to have an angle like this. Okay, we can have alpha and beta. Okay, and this is a straight line. Okay, and in that case, alpha plus beta equals 180 degrees. Okay, because together they make up a straight line. So these are called supplementary angles. I don't want to try to spell angles again. I would screw that up probably. And then last but not least, we've got these, if you have two parallel lines and you've got another line that crosses them, one of the things to note is that if you know one of these angles, if you know this is alpha, okay, and I don't remember what these terms are for these angles, then you know that this is alpha. And from that, you know that this is alpha. From that, you know this is alpha. Okay, which is a pretty cool thing to know. The other thing that is nice to know here is that this is, let's suppose that's beta. Okay, we could use all the exact same logic to know that all of these are betas. Okay, and then notice that from this and from what we learned, from what we have up here with this, okay, that alpha plus beta equals 180. Okay, and so that's kind of the last of the angles. The last thing that I want to put in here, and this will be really quickly, and this is really not a geometry, I mean, it is geometry, but it's more of a units thing because a lot of you haven't thought about this before. And this is something that shows up a lot. And so I'll ask somebody, they'll come to my office and we'll be chatting about help stuff, and I'll say, okay, what's the area of a circle? And they'll say, ooh. And they'll say one of two things. They'll either say 2 pi r, or they'll say pi r squared, okay, where r is the radius of the circle, okay? And so what I want to point out here is how you would know which one is which, okay, or which one to use. And sometimes they'll say 2 pi r squared, but that's just not an option, or not a correct answer in any universe. So anyway, so if we're choosing between these two, the way that you're going to know is quite simple, okay? Or, simple may be the wrong word, but if I'm going to, let's suppose I were going to solve this number. So what would I put in for r? Let's suppose I have a circle, okay? And it's got a radius of like, 10 inches, okay? So I'm going to plug it in to both of these formulas, and I'm going to see what comes out. Well, in this formula, I get 2 pi times 10 inches, so I get 20 pi inches. If I plug it into this one, I get 10 inches squared, that's 100 inches squared, times pi, so I get 100 pi inches squared. Oh, that's interesting. I think I may have stumbled onto something. Notice, in this one, I squared the inches. In this one, I did not. Okay, so I ended up with square inches, and here I just measured inches. So which one of these do you think is the area? Okay, just so happens that this one is the area, because I square the inches. Notice this one is the circumference of the circle, or the perimeter of the circle, so the circumference. Okay, what do you think is going to happen if I look up the volume of the circle? You guessed it, 4/3 pi r cubed. Okay, so if this were a sphere up here, okay, then I would get 10 inches cubed, which would be 1,000 inches cubed. So I'd get 4,000 over 3 pi inches cubed, okay? And clearly from that, it would be a volume, okay, because I get inches cubed. Okay, and this can go for anything. Like if you were looking at let's suppose you were looking at a rectangle, okay, or a rectangular solid or whatever, the circumference of that would be, if this is length and this is width, it would be 2 length plus 2 width. Okay, notice now whatever I put in there, I've got inches plus inches, I'm just going to end up with inches. Okay, if I did the area, I would have length times width. I'd have inches times inches, so I'd have inches squared. This would be just inches. And let's suppose now it were a, a solid, length times width, and well, we'll call that height, whatever. The volume would be length times width times height. Well, now we've got inches times inches times inches, so we'd end up with inches cubed. Okay, so just something to be aware of. It'll help you smooth out some potential problems you have as you move through engineering. Okay, so we're about 25 minutes, so that's pretty much, that should be like 95% of the geometry that you'll need. Some other things I'm sure will show up here and there, and we'll talk about them as we go. And if you need any help, just come find me. All right, hope y'all doing well. Okay, bye.